Good afternoon, everybody, and welcome to the EMB Third Thursday Science Webinar series. So my name's Bert Alexander. I'm a science officer here at the European Marine Board, and I'll be the moderator for today. So before we start, we'll just go over some housekeeping rules. So make sure that you have your name clearly entered so that when you ask questions during the Q&A session, we know who you are. And you can put your question in the Q&A box. So the chat is just for if you're having any technical issues, but yeah, all of your questions should go in the Q&A box so that I can see them. And then I will select which questions to ask to our speaker. And you can also let us know which organization and country you're from. And just for your information, this webinar is also being recorded and it will be available afterwards on the EMB YouTube channel. So the talk today is about distribution models and habitat mapping for the application of an ecosystem approach to management. And this is linked to the European Marine Board Future Science Brief number 11 on marine habitat mapping, which was launched in June earlier this year. And our speaker will be José Manuel González Irusta. So he was a member of the working group on marine habitat mapping, and he's also a researcher at the Spanish Institute of Oceanography. And yeah, just a welcome also to his colleagues who are joining us in the webinar today. So I will pass over to you, José, then. To let us know a bit more about your work.
Thank you very much, Britt. I will try to share my screen now. Are you seeing my screen correctly?
Yep, it looks good, thanks.
Perfect. Then I will start this seminar talking about what basically has been the main topic of my work in the last 15 years, distribution models and habitat mapping for the application of an ecosystem approach. As you probably know, the ecosystem approach to the management of an ecosystem aims to evolve for a management based mainly on specific approaches, stock assessments basically, which has been or was at least the type of management of the ecosystem that was done until the basically last years of the last millennium, to other management more holistic, where other features of the marine ecosystems are also considered: habitat quality, prey abundance, etc. The necessity of this approach has been also announced for the growing number of impacts present in the marine ecosystems, which has also evolved for basically one main pressure, fishing, through the current scenario when we have to deal with many other pressures such as pollution, eutrophication, offshore developments, alien species, and all of these surround for a global challenge such as climate change. This evolution has been also reflected across time in European legislation. The first important directive at European level that basically implement the ecosystem approach in the marine ecosystems was the Habitat Directive, which has been the umbrella under which most of the MPAs across Europe has been developed. In 2008, Europe approved the Marine Strategic Framework Directive, which has been absolutely key as well for the implementation of this ecosystem approach with the 11 descriptors that probably many of you know, such as seafloor integrity, marine litter, pollution, etc. Of course, the Marine Spatial Planning Directive, and very recently, just this year, the Nature Restoration Law, a very ambitious piece of legislation that I think is going to be very important in the next decades, I would say. And basically, all of this legislation have something in common, and what they have in common is that they need maps. They are obliged to basically start to provide outputs that are spatial. In general, what we are obliged to map more often is habitats, benthic habitats, but before talk about this, I would like to clarify some concepts. Habitat is a polysemic word with at least 3 different meanings that unfortunately are missing in the frame of habitat mapping, which generate confusion. So I would like to start talking about these three concepts. The first concept in which we can use the word habitat is as a synonym of niche, describing the multidimensional volume formed for the biotic and abiotic factors that drive the life cycle of one species. We will talk a little bit more about this later. The other concept, meaning of the word habitat is when we use this word to describe a particular combination of abiotic factors that usually host similar communities across the space. And this will be the case, for instance, of the EUNIS habitats 2 and level 2 and 3, things such as Atlantic and Mediterranean high energy infiltral rock. And finally, there is a third concept or a third meaning of the word habitat. That is when we use this word to describe a biological community that provides shelter to other organisms and therefore is considered to be a biological habitat. Things such as deep sea spongy grounds, shipping fells, marsh grounds, these kind of habitats. So how we can map these habitats? Well, for the broad habitats, what we are doing, thanks to hierarchical classification of habitats such as EUNIS, that I think is very clever, by the way, is we are mapping these habitats by basically mixing 4 different GIS layers: depth, substrate type, energy, and biogeography. Because if you see this habitat here, Atlantic and Mediterranean high energy inflatable rock, Atlantic and Mediterranean is a concept which is related with biogeography. High energy is clearly referred to energy, a layer of energy in the seabed. Infralittoral is related with depth, and rock with substrate type. So basically, by combining these 4 layers, we will be able to generate a layer with the EUNIS 2 and EUNIS 3 habitats. If we want to model biological habitats, the things are much more complex. We can use direct methods. Remote sensing can be used to directly map the distribution of intertidal and shallow bending, but that's the problem. We only can use direct methods for very shallow habitats, depending on the transparency of the water, from just a few meters to maybe 20 meters. But even 20 meters is not too much when we talk about the marine ecosystem size. Most of the areas of the marine ecosystems are deeper than that depth. For everything deeper than 20, 30 meters, we need models, basically, not direct methods. And for doing that, for mapping these habitats, we can do different data quality or different response variables. We can use presence data using only presence, although most of the cases when we talk about only presence, we are talking really about presence and pseudo absence or presence absence. We can use abundance data, or we can use community data. Of course, as more complex are the data we are using for the model, also more complex are the models. So, broad habitats. If you go now to EMBONet and you see the portal of habitats, broad habitats of EMBONet, you can find something like this map here, and you may have the sensation or the feeling that all the work is done. Well, this is not true at all. The quality on bathymetry is very different between regions, and also within areas, between areas within regions. And you still can have important surprises using EMBONet bathymetry, such as loose and small seamount or small band, more than seamount. Of course, seabed bottom time is very bad in some regions as well. The region I know the best, the north coast of Spain, for instance, the rocky layer is not good enough. But also there are a lot of areas of this map that you are seeing here when the substrate type is seabed. Seabed is not a substrate type. Seabed is an NA value, okay? So even when you see the map looking complete, it's not complete at all. So it's necessary to improve both habitats, not only to improve the broad habitat layer, but also because by improving our knowledge about substrate type, depth, etc., we can also do much better habitat mapping for biological habitats. The second concept I would like to introduce in this talk is the concept of distribution models. Distribution models, also called specific distribution models, habitat suitability models, or ecological niche models, are a group of terms which usually are applied indistinctly, although they have small meaning difference. But basically, we'll use these terms to refer models that allow to predict the spatial distribution of a response variable, usually species presence, but can be something else, based on a set of explanatory variables that are variable, at least for most of them, in a GIS format. I will explain this a little bit better later. Despite the frequent indistinct use, these terms name different concepts depending on what they are modeling exactly. According to Merino et al., ecological niche models aims to estimate fundamental niches of a species, whereas species distribution models attempt to estimate objects in geographic space. And I will try to explain this better using this graph here. This graph, also started from Merino et al., shows you the three main drivers which define the distribution of one species. We have the abiotic drivers, so the temperature at which the species can survive, the depth in which you can find it, the salinity which that species like to or prefer to for living. That will be the abiotic factors. Then you have the biology, the biotic factors, things such as prey availability, predation, these kind of things. And finally, you have something referred to motility, but also to the geographic history of the species, where the species was generated. The combination of these three factors or group of variables define the ecological niche of the species, G1 and G0. But inside this area, you can have an area which has been occupied by the species and other that has not been. And this can be very easily understood looking at this map. In this map, this is output for the Atlantic project when I modeled the distribution of Lophius budegassa. Lophius budegassa is the monfish, and it's a species of monfish that only can be found in the east part of Europe. If you see the outputs of the model, however, you will see that there is also suitable areas in the west side of the Atlantic. And this is not because the model did a terrible work. This is because actually these areas are environmentally very similar. The only reason why monfish is here and is not here is because at some point the monfish in both sides of the Atlantic diverge and turn into different species. So coming back to the difference that Merino et al. Do talking about distribution models, if we call out ecological niche models, we should do this kind of work. But if we are talking about the species distribution model, we should use models that only identify areas when you can find the species. However, in most of the cases, if you work in an area small or not that big as the whole Atlantic, both things will be the same. And that's probably one of the reasons why most of the people don't do this distinguish. In any case, I explain it because I think it's good to know. Furthermore, according to this author, Merino et al., it is possible also to distinguish between three categories of models, depending if they are correlative, mechanistic, or process-oriented models. In fact, 95% of the models, I didn't do the maths, but something like that. I mean, a big majority of the models are correlative models, and these are the models I'm going to explain here today. So how they work, how the distribution models work. Well, usually you have two types of that. You have samples for which you know the longitude and latitude, so you know the position, and you have a set of environmental variables in a GIS raster, in a GIS layer, usually a raster, okay? So then you can use the coordinates to extract the value for all of these variables in these positions. And by doing this, you can generate a data frame such as this, in which you have the coordinates of your samples, the response variable of your sample, which can be present absence, can be abundance, but also can be an index, or can be longevity, can be whatever you want. And then the value of the explanatory variables in these points. Then, as in any other analysis we do in biology, we will correlate using a statistic algorithm the response variable with the explanatory variables. You can use here GAMs, ELMs, GLMMs, you can use random forest, you can use max, and you can use whatever you want to basically correlate the response variable with the explanatory variables in an equation. And then the final step is to apply that equation to each cell of the rasters, because as we have the explanatory variables in a raster, we have information for each cell, and then we can produce the map. And it's exactly this, the map, which turned these models in something so popular at the moment. I mean, in the past, some people say that this will be a fashion thing that was 15 years ago, and I think distribution models are more fashionable than ever. So I think it's definitely not something fashionable. So we can use distribution models, as we will say here today in this talk, for many things. but probably the most obvious thing for use them will be to basically having problems here. To use them to model the distribution of one species. So use the habitat concept as a synonym of niche. The first papers that were published in Marine Ecosystems did exactly this. This is a paper I like especially because it's the first paper I read about distribution models. It was lead for my colleagues from ASTI, Yvonne Garpasoro, and it's a very nice paper, especially because it was a pioneer. In this work, they modeled the distribution of European lobster, Domarus gamarus, in the Basque Country, and they not only find new fishing grounds for the fishermen of the Basque Country, but also they saw how we can use these models in the marine ecosystems. Of course, there are many other examples. Probably one of the most typical use of these models when we are modeling one species is to model the distribution of charismatic fauna. I choose this paper from white sharks, not only because I love white sharks, but also because I was trying to ruin your holidays in the Mediterranean. Because as you can see, according to this model, the white shark can find suitable areas in many places of the Mediterranean, which is a little bit scary if you think about it. And then, of course, we can use this for many other things. This is another work we did in Azores when we modeled the distribution of 14 different species of deep sea sharks in the Azores Islands in order to find hotspots of these species, trying to avoid bycatch of the bottom long line of the area. Of course, we can use distribution models for mapping biogenic habitats. For doing that, as we say before, you can use different response variables. You can use present absence, you can use abundance, or you can use community data. This is important for listed habitats such as vulnerable ecosystems, but also, for instance, if you want to develop the management plan of an MPA, the first thing you need to know is what you have in this management in that MPA. For that, you need to do the maps. Okay. So we can use presence absence, but of course, this has some problems. And the problem is that one species can form an habitat, but it's not the same to model the present absence of the species than to model the habitat. This is something that Howell and others present very nicely in this paper in Biocar Conservation from 2011, when the species is also an habitat, comparing the predictivity model distribution of Lophelia pertusa and the reef habitat it forms. So these authors demonstrate that it's not the same to model the colonies of Lophelia pertusa than the reef of Lophelia pertusa, and that basically they suggest that if what you are interested is in protect the Lophelia pertusa reefs, that's exactly what you have to model, not the Lophelia pertusa presence, but the Lophelia pertusa reef presence, which is not the same. Of course, that opens the question of how we can model, how can we define reefs or BMEs. And for that, there are different solutions. When the habitat is formed for only one species, it seems clear that the best thing to do is to model the abundance and then use the abundance as a proxy to the habitat. That's exactly what my colleagues from IO Santander, Augusto Rodriguez Bázalo, and others did in this paper from 2023, I think it is, when they mapped the distribution of several BME species in Naviles Canyon using delta gams and modeling the abundance of the habitat forming species. The other option is to use community data. So basically, because sometimes the habitat is formed for only one species, but sometimes it's formed for several species. And when this happens, the only possibility to model the habitat that this species form is to use community data. And as we see before, there are three possibilities to do that. One of the approaches is called assemble first, predict later. The other is called predict first, assemble later. And the third one is basically all together, to use sophisticated models that allow you to do everything in just one step. The first approach, assemble first, predict later. The first time I saw this approach in the marine ecosystem was in this paper of Charlotte Maurice from Canada. And then we apply it in two different works, one in the Galicia Bank and another one left for my colleague, Ana Torrenta, as part of her PhD that already finished in the Seco de los Olivos. I will talk about the last one because it's a paper and a work I like especially. In this work, we have a very intense and nice sampling effort in Seco de los Olivos. This was the rock transit that the NGO Oceana did in this area. As you can see, it covers basically the whole seamount. And thanks to this very good data, we were able to do a nice assemble analysis to define up to 13 different clusters of biological species, of species that appear together, generating different biological communities. Once we define the assemble, we did the prediction of its distribution in the seamount, and we obtained, of course, different outputs for each of the assembles, and we combine them in this kind of output, which is, I think, a very nice output if you want, for instance, to develop a management plan for an MPA. You can see what kind of habitats you have, then you can overlay these type of maps with your fishing effort and make decisions about what you are going to allow, what you are not going to allow, what areas you are going to protect, and what areas maybe you will protect less. Of course, even when the video is very nice and it gives you a very appealing output, probably it's more correct to offer this other type of output that we offer 2 years later in this paper in marine policy, when we use 2 different thresholds. And just by changing the threshold of the models which are behind these maps are the same, but we just change the threshold. You can see that in the left, the biological habitats are much more bigger than in the right. So the intense colors are biological habitats and the brown colors are growth habitats. As you can see that just by changing the threshold, the map changes quite a lot. So this is also something important to keep in mind. We are not talking here about satellite images in reality. This is models. The other approach we can use is the contrary: predict first, assemble later. In the best of my knowledge, I only know one work that did this in the marine ecosystems. It was this work published in Frontiers Marine Science for my colleague Julian Burgos. Julian, with his colleagues, have a very nice database with a lot of information up to, from the Nordic Seas, up to 44 indicator BME taxa. And they use the presence records of this taxa and background data to run 44 different maxim predictions, and then they use the maps of these predictions to do the assembles. So instead of do the assembles first, they find the communities and then model that communities, they do either the other way around. They model the 44 species they have presence in the area, and then they did the assembles from the maps. The outputs are similar. It's basically the outputs of the different assembles, but this is only to show you that we can do things in different ways. Of course, these approaches have caveats and limitations. Some of them are quite important. These techniques can predict assembles that never occur in nature. That will be a limitation mainly related with predict first, assemble later. It is possible to predict overlapping of habitats that does not occur in nature. Each model is fitted independently to the others. The other probability in each cell does not necessarily add up to 1. And it's not possible to calculate the uncertainty associated with the 2 model steps jointly. So, because, I mean, we do this in 2 steps, but the 2 steps are not connected. That means that the probability of all the models we are modeling or predicting not necessarily add 1 in each cell, and also that we cannot map the uncertainty associated to the whole process. This is something that somehow is resolved for the third approach possible, which is to do it all together using this kind of models, such as joint species distribution models. These models are quite recent in comparison with the others, has been around for around 10 years. But now there are quite good examples, including some in the marine ecosystems, and even a book that you can read it. But of course, they also have caveats and limitations. They can be very complex. I have been trying to use these models for a while, but I never find the time to go into them. And one of the reasons is because I think it will take a lot of time, because they are not especially straightforward, although I have looked enough to be in a course last year, and I hope I will finally manage to go into them. And more importantly, they are very data greedy. So you are going to need a lot of data, good data, if you want to use these models. However, there are already some very good examples of this. This is a paper which has been published just a few weeks ago for Javier Murillo from Canada. They use a very nice data set from troughs from the Canada continental shelf. And with this information, they managed to define up to 8 different assembles and to map them. And the kind of outputs that you can see here is similar to the outputs we saw in the Seco Los Olivos, but this is, from a statistic point of view, has been built in a sounder way, if you wish. So we have seen how we can use distribution model for model species distribution, for model biological habitats, but of course we can use distribution model for many other things. And one of the more relevant things at the moment for which we can use distribution models is to forecast climate impact in biodiversity. As you remember, when we do a distribution model, we extract the values of the environmental variables from the locations, we generate a data frame, we fit an algorithm, and then we apply back this algorithm to the layers. But when we do this last step, we can change the present layers for future layers. So we have, for instance, temperature, salinity, aragonite, and oxygen for present conditions, but also for future, for 3 different scenarios of climate change. We can, in this last step, change the present layers by the future layers. And by doing this, we will be able to forecast how, according to these abiotic variables, the species are going to change its distribution. So this is exactly what we did in this work that we published in 2020. This is a paper that was led for Telmo Morato. I was involved in the development of the models. And basically in this work, we modeled the distribution of 6 species of corals and 6 species of fishes, deep sea fishes. And well, you cannot see too much. This one here, this column, are the present conditions, and this one is the prediction the models did for the future, for corals and for fish. We also model the loss of habitat, the gain of habitat, and the refugee areas, so areas which are suitable now will be suitable in the future. And well, as you can see here, there was a lot of red. I have to say that we used the most pessimistic of all the possible scenarios, the H.5 for 2100. But it's also true that corals are facing a very challenging scenario, because the problem the reason why we have all of this red, it was that we have this double effect. Temperature is sending corals to the deep sea, to deeper waters, because they are cold water corals, so they don't like the warm, they need cold waters. But at the same time, the acidification is making that the aragonite saturation horizon will be shallower decade by decade. So basically, his suitable niche is being narrowed, and this is what it was shown in this work. Of course, we can forecast the future, but we can forecast anything else. And one thing that I think is very interesting at the moment, especially in the frame of the restoration law, is that we can try to predict the past in order to be able to compute habitat loss and reference areas and reference conditions. That's exactly what we did in this paper that we published in 2022, mapping habitat loss in the deep sea using current and past present of Isidela elongata. In this work, we have a very nice data set from my colleague Joan Cartes. Basically, we have in red presence of Isidela elongata, in white absence of Isidela elongata, and more nicely in orange. There are some points here in orange, if you can see them. We have rest of death colonies of Isidela elongata. And by using this depth and by using traveling layer, we were able to use 2 approaches to try to predict the habitat loss of Isidela elongata in this area of the Spanish Mediterranean. So we have a lot of environmental sets, such as depth, currents, type of sediment, but also, more importantly, we have trawling effort in the area. So we use 2 approaches. In the first approach, we use only current presence, so we don't use the death colonies. We include trawling effort as explanatory variable. We use real absence, and the points where the only Isidela elongata we find was a death colony was considered an absence as well. That will be approach 1. In the second approach, we did not include trawling. We use pseudo absence because, I mean, we didn't use real absence because real absence can be affected by traveling. You have an area which is actually suitable for Isidra elongata, but has been basically, there is no Isidra elongata because traveling has eliminated all of them. To include this absence, we confound the model. So we use instead pseudo absence as a less evil. And we also use, more important, the records of Isidra elongata, the death records. So the records of Isidra elongata that were not alive when we catch them, but they were alive in the recent past. Well, this work gives us quite interesting results. One of the results is that there is a clear proof of that Isidra elongata have a truncate niche in the area. Because, for instance, the depth peak, it was much more deeper in the first approach than in the second one. So when we use the death colonies, it seems that the peak in depth of Isidra elongata is shallower. And this is related with the fact that traveling is basically removing Isidra colonies, especially of the shallower part of his distribution. The other interesting thing about this is that we were able to compute maps of habitat loss. For doing this, we mapped the current distribution of Isidra elongata using traveling effort. This is this map. Yeah. So this map is the result of the first approach. And then we did another two maps. This map is the same model that built this map here, but modifying the traveling layer and replacing all the values by 0. So this will be a scenario with no traveling at all. Using this model, but with no traveling at all. And this other map is the result of use the deficit Isidra colonies. By comparing this map with this map, we can obtain this level of habitat loss. And by comparing this map with this map, we can use the other type of habitat loss. So we can obtain two maps of habitat loss that we finally combine in a final map with no habitat loss, areas classified as no habitat loss in both figures, with habitat loss with high uncertainty, areas classified as habitat loss with high uncertainty in only one of the two figures, and with habitat loss of medium and low uncertainty, being habitat loss of low uncertainty, areas classified as habitat loss in both figures, at least in one of them with low uncertainty. I'm running out of time, but there are many other application distribution models. We can use distribution models to help in the assessment of non-indigenous invasion risk, as this paper here for Leidenberg and others, to model essential fish habitats, to complement and improve stock assessment models, to model other response variables, because, I mean, I didn't highlight this enough, but distribution models can be used not only to model present absence or distribution of species or habitats, but also to model any other type of response variable, an index, and isoscapes, etc. Of course, we can combine these models with other type of models, such as track particle analysis, to inform our connectivity. And very importantly, although usually you won't find many papers about this, but we are currently using, and we can use these models to survey better, to inform new surveys. If you want to know more about marine habitat mapping and distribution models, I highly recommend that you look into the report we did in the framework for European Marine Board about this topic with this fantastic college. And before I finish, some take-home message. Distribution models are very powerful tools, key in the implementation of the ecosystem approach to the management of marine ecosystems, if they are appropriately built, but they are models. Therefore, sitting by these mathematicians, they are all wrong. It's also true that sometimes they are also useful, but they are all wrong. What I want to say with this, but we need to reduce expectations. Managers need to understand that a model from the seabed, regardless how good it is not the same as a satellite images from an ecosystems. And therefore, we cannot do the same that in terrestrial ecosystems. We can generate proxies to the reality, but they are just that, proxies. Regardless how sophisticated the model is, it never will be better than the data used to feed it. We still need monitoring. More ambitious management target also need more and better monitoring. I would like to finish this talk to encourage people involved with the world of marine habitat mapping and distribution models to join us in the working group of marine habitat mapping of ICES. We are a nice and active community, but we are looking for more colleagues. So if you work on this and you have the opportunity, please send us an email to me or to ICES, and we will let you what to do. Thank you very much. Muchas gracias.
Thanks, Jose. That was really great to really dive into this topic, because it was something that was touched on in the Marine Habitat Mapping Future Science Brief, but we didn't go into huge amounts of detail on it, and it's really fundamental to habitat mapping. So you can keep your camera on, Jose, as we go to the Q&A. So I will just remind everybody to please ask your questions to Jose in the Q&A box, and then I will read them out. So we already have one question from David Connor, who actually was one of the reviewers on the Future Science Brief, and he's a consultant and was formerly part of DG Environment and was involved in building UNIS and the EU CMAP. So his question is, how can habitat modeling and mapping contribute to improving the UNIS classification, where the 4 main sediment classes, so coarse, mixed, sand, and mud, are not always well aligned with the communities at lower UNIS levels?
Yeah, well, that's a tricky question.
Yeah, we can hear you now.
It's a tricky question. I mean, I think one of the things I would like to do definitely is to apply these kind of models we see in the talk, the community models, and see if there is a good agreement, at least for our area, between the EUNIS 3 and the communities we see in the biological habitats. And if they are not, to try to dive into, I mean, to understand why not. But at the same time, I mean, we can always work for improving EUNIS 3 habitats, but we are always going to need them, because they are assessment units that doesn't change with time. And that's something that biological habitats doesn't provide. So I think it's, we have to work to improve them. And I think one of the ways to do that is to start to map biological communities and try to see how good or not they agree with the EUNIS 3 habitats. And if they don't, try to improve EUNIS 3 habitats in that direction. But at the same time, I think it's important to keep them.
Yeah, thanks. So hopefully that answers your question, David. So I have a question as well. One of the recommendations from the Future Science Brief was to work on developing best practice documents on how to select the type of model to use for specific applications, because you've presented a lot of different models and a lot of different applications. So like, how does somebody go about deciding which one to use for their specific application? And you also it said in your last slide that the ICES working group had developed standards for models in 2021. So, but I suppose that's not really a sort of best practice guide for actually how to use those models for specific use cases. So yeah, I'm wondering if there's any progress on that recommendation, or how that could be implemented.
Yeah, so the guide ICES did, it was very kind of modeler guide. So it was kind of follows some papers which has been already published mainly for land ecosystems. And basically the idea is to have some kind of standards on how you have to build a distribution model to be considered statistically sound. Things like, you know, taking account the geolocation error when you decide at what resolution you are going to work, try to use more than one algorithm if you can, always do cross-validation, and if possible, using space blocks, these kind of things, which are very for models. What we tried to do in the European Marine Board, it was more kind of general, not for modelers, but more for like policy makers and users of the map. So this is totally different approach. And For that, I think it's more tricky because quite often what you want is not available. That's the problem we usually have. So I think if you ask us, for instance, for BMEs, I'm quite involved in BMEs. If you ask me what we need for do a proper, to advise European Union on how to protect these areas, I think we should do specific models for that. But the thing is that we don't have that model. So quite often we try to use models which has been already published. But the problem with that is that quite often that model has not been published or has not been created for exactly that purpose, or maybe they use the presence of the BME as a proxy to the habitat, or maybe that doesn't cover the whole area you need in your advice. So that's the problem, that quite often there are hundreds of models out there, but quite often, in spite of this, it's very difficult to find the one that you need for each purpose.
Yeah, and is that something that the ICES working group will maybe work on or is thinking
Yes,
about?
we are now actually our last course. It was of last year. It was to basically identify what are the main limitations, which explain why these models are not too much used in, for instance, ICES advice, and try to propose solutions for that.
Yeah. Okay. So I see there's a lot of questions coming in the Q&A, so I'll move on to those ones. So we have Dylan Earl, and he's asking, do you have a preference for choosing modeling tools? So ENFA, Maxent, or Random Forest, for example.
Yeah. Well, I mean, I don't, and I shouldn't advise any of them over the others, because which already exists is an agreement that there are at least 2 or 3 that are comparable. So, I mean, the reason why not everybody's using the same is because there are not clear, data that justify choose one over the others. My personal preference is GAMS. I always try to use GAMS, and then, if possible, complement with Random Forest or Maxent. I can go further on this, but I think maybe it will be too technical. I don't know if...
He says, I see he's added a second question, as he wants to know if, for example, one is more suited for a particular modeling application versus another.
Yeah, so for instance, for using only presence, the one I always try to use as well is Maxent. But in fact, you don't use only presence, you use pseudo absence, and you need to think a lot on how you generate pseudo absence. So more than the algorithms, my advice will be try to always use presence and absence if you can. That will be my first advice. And only if this is not possible and still you want to do the model, think on use pseudo absence. And be aware that even Maxent generates pseudo absence. They call it background points, but they are pseudo absence. And even if they don't tell you how they generate them, they generate them. And because of that, the background selection will be very important in everything you do. So be always very, very, think a lot about pseudo absence if you are going to go with only presence models.
Okay, thank you. So we'll move on to the next question from, we don't know who this is from, but they say they would like to hear more about how you generated the 3D image and the video of the BMEs.
Yeah, well, I didn't do that, but this is a tool in GIS. So I think they did it with ArcGIS. It's not R. But so basically, we provide the map, a map as the map I show in the next slide. So a continuous map with the different biogenic habitats, and then they load this in ArcGIS, and then there is a tool in ArcGIS. I don't remember exactly the name, but I think if you Google it, you will find it, because it's ArcGIS, and I think it's not too difficult.
Yeah, great. So we have a question from Pedro Escuerdo Lozano. He says, which studies would you recommend to start working on modeling densities? Would you use a suitability index from a PA model as an independent variable in these models?
About the first question, I mean, there was some, when I started working in Abundance, I have worked a lot in Abundance with fish. to model essential fish habitats, so spawning grounds or nursery areas. I didn't have the time to talk about this in the talk, but this is the kind of abundance models I did the most. I have probably like 4 or 5 out of this. And before these papers, I used actually the work of Sandrine Bass. So she was not the first author, but it was the last. I don't remember the name of the first authors, but it was about the spawning ground. So if you want to start to model in abundance, I will suggest to look for abundance models of fish because they are quite good. And about the second question, I didn't understand really. Can you repeat maybe?
Would you use a suitability index from a PA model as an independent variable in these models, also still related to modeling densities?
I don't know if I understand. If it means, I mean, you can use outputs from another model, for instance, if they are a prey. So if you think you have a model which show the distribution of the prey of your species, and you think that the distribution of that prey can actually drive the distribution of the species you want to model, then it makes sense to use that model as an explanatory variable. Yes, why not?
Yeah. Okay, it's good to share your expertise here. So we have another question from Sienna. She says the MPA advisory group in Ireland has largely excluded habitats protected under the Habitats Directive from the criteria it uses to include habitats and species for protection within proposed MPAs. Given that the Irish Sea Annex 1 submerged sandbanks host many habitats that come under the Habitats Directive, is this an advisable approach in designating MPAs? Ireland has already granted foreshore permits to 7 large inshore wind turbine arrays, phase 1, not subject to SEA on sandbanks.
Yeah, I mean, I don't know really how to answer that. I mean, Ireland has a fantastic habitat mapping program. They are leading country on this. They have mapped already his huge EEZ in terms of bathymetry, so they have very good bathymetry, and they have all the information they need to do very good habitat mapping. So I guess this may be a possibility if they also have good monitoring for biological species. So I know they have enough environmental information because I see them. If they also have good biological information, definitely they can use this kind of approaches to generate, to map his biogenic habitats. And this will be information that for sure will be useful for any management plan for any MPA. I mean, if you want to do a management plan, you need to know where are the things you want to manage. I mean, it's pretty obvious, so you need maps.
Yeah, so hopefully that helps to answer your question, Sienna. Okay, so I have some questions from one of my colleagues here as well at the European Marine Board. They're in the chat, not in the Q&A. So Angel is asking in terms of modeling and mapping, what should first be improved in order to inform and implement the nature restoration law?
Sorry, say again.
So in terms of habitat mapping, so what are the priorities for mapping and also, I suppose, improving the distribution models if we want to, given the new nature restoration law? Yeah. What are, from your opinion, what are the key priorities for mapping?
Yeah, I mean, the key priorities will be the habitats that are listed in the restoration law. They list several habitats for different areas. And the priorities should be first to model the current distribution of the habitat, which is tricky enough and difficult enough. But then I think, because I mean, I am not an expert on the restoration law, but I have the feeling that they are pretending that we also try to suggest what was the past distribution of the habitat.
Yeah.
And then we have to try to restore the habitat to something similar to that original conditions. And I think this is going to be incredibly complex. Because as I say, for instance, in the habitat, in the paper of Isidra Longata in the Mediterranean, trawling has been around for decades. And the habitats we see, the communities we see, the biological communities we find when we go out there are the result of decades of fishing. So they are not pristine at all. They are very far to be pristine. In other areas, such as the Baltic and the southern North Sea, you also have eutrophication, pollution, wind farm builds, aquaculture. So with all of this, to try to map the current distribution of this habitat is tricky, but try to predict where these habitats were in the past and are not any longer is near an impossible mission. So I think this is what is going to be very tricky, and we need to, of course, do a bigger effort and try to help from the modeling part, but at the same time, we need a certain level of realism in the managers about what is possible and what is not.
Yeah, that's interesting. I didn't realize they also wanted so much detail on the past states.
That's what is unclear to me. They want, but if you talk about restore, I mean, it's restoration, right? So you want to restore something that is not there anymore. Because biogenic habitats, people maybe feel that they can degrade slowly, but in general, in relation with trawling, this is not what happened. They are or they are not. That's what happened with what you can find after trawling is some survivors of the species which in the past formed the habitat, but not the habitat anymore. So if we want to restore, we need to find the areas when the habitat was in the past. And that's not going to be easy, because what you don't want to do is a lot of effort to restore an habitat in an area where never was, because probably never will come back. So the first thing you need to restore something is to be sure that that area is suitable for the habitat.
Exactly. It's a big challenge.
It is a big challenge.
So I have one more question as well, also related to some of the recommendations from the Habitat Mapping Future Science Brief. So there's quite a big section in the document about uncertainty in habitat maps, and also like related to your statement on the last slide that it's just models and there's always some uncertainty in there. So we talk in the document about the importance of communicating that well to end users, so that they, like you also showed in your presentation, by changing one variable that can really change the predicted distribution of the species quite significantly. So can you talk a bit more about, in terms of the modeling, how is uncertainty in the models, how at the moment is that communicated to the end users, and do you have some ideas for how to improve that?
I mean, the first thing about uncertainty is that there are very types of uncertainty associated to a model. Some of them can be mapped and others cannot. So the uncertainty which come outside from the model process, the standard error associated to the prediction, that can be mapped. And I can give you a map with the prediction of the model and another map with the standard error associated to that prediction. Which cannot be so easily mapped, usually it's not mapped at all, is the uncertainty with every decision which has allowed you to build the model. Things like, okay, I'm using this depth layer, but I know this depth layer is not that good in this area as is in this area, or this current, I'm going to use this climate change model, but I don't have a clue if the climate change model for the future is super good or not that good at all. I mean, all of these kind of things that are around the models. So, and when you put all together, there are a lot of uncertainties. So I think what we need to be here is not really, I mean, we have to do a lot of improvement on how we map the uncertainty, and we have to do a better job. But for me, the most important thing is that everybody understands that when you work with models, you are not working with the reality, because my feeling is that we are more and more pretending that we can replace satellite images from land ecosystems with the models we generate for biological habitats. And that's not possible, and I think will never be possible. And that's something that I think we need to, especially because restoration law are this kind of other big challenge. We need to start to understand that we can do a lot of things, but we will never have a complete picture in real time as we can have in land ecosystems.
And I think the last point you had on your slide is really important, just reinforcing the importance of continued monitoring as well, to improve the models and improve the training data.
Yeah, I mean, when I was working, for instance, this work I did about climate change with fish and with corals, work with fish was much more easier because we have thousands of data. I mean, for fish, we have, I mean, millions of data. I remember for goat, I have millions of data. Just by drawing the points in the map, I already have my suitable map. So if we have very good monitoring, or if we continue improving our monitoring and we start to have much more data, we can do much more things for sure.
Okay, we have one more question from Owen Clarkin. It's quite specific to the nature restoration law, so I'm not sure you'll know the answer, but we can try anyway. So in terms of biogenic reef habitat restoration, is it also important to protect the species which may not be reef areas in order to provide genetic diversity for restoration of potential reef areas? And is that covered in the nature restoration law?
Yeah, I don't know if it's covered in the restoration law. I mean, I work a lot with traveling impacts, so I usually quite biased for this particular pressure. For that particular pressure, if you protect the reef, you protect everything else. And I think in general, this is quite the case for most of the pressures. It may happen for pollution or eutrophication that this is not the case, but for most of the cases, it will be the case, physical pressure for sure. So in general, one of the reasons why it's so important to protect these habitat forming species is because by protect them, you immediately protect the habitat they form and therefore everything which lives inside.
Yeah. Okay, so we're almost at the end. So I will thank you again, Jose, for your time today. And yeah, it was really nice to hear more about your work and to get some more insight into this really fundamental aspects of habitat mapping. And thank you to everybody who joined us and using your last days before Christmas to learn more about habitat mapping and distribution models. So I hope everybody has good holidays, and I will just share my screen again because I have one more slide to announce the next webinar. So our next webinar will be on the 16th of January. So we will have Renske de Winter. She was a co-author of the Ocean and Climate chapter of Navigating the Future 6, which is the EMB flagship document, which we just launched a couple of months ago in October. And she will be talking about how to prepare for the future and scenarios for future water conditions and sea level rise adaptation strategies from the Netherlands. So that's now open for registration. So yeah, we'll see you in the new year, and thanks again to Jose and everybody who joins.